Okay. So, hello everyone. My name is Mattia Manzati, and today we're gonna have a journey into the world of computation. And today we're gonna see what's the current state of the art of defining computation with JavaScript. We'll see which are the problems you may have right now in your application and you don't know about. And finally, we'll see if you are satisfied with the current state of the art and if there's room for improvement. So, what a better way to acknowledge the current state of the art than building a real application? So, I think let's try something different. Let's build something no one has ever built. So, let's build together a to-do application. And, well, our to-do application will be very different from the other one. We have a user with a username, and we have a to-do, and the to-do will have an assigned user, and a title, and maybe eventually marked as completed. So let's see how much time it takes to build this application. So it's a new week, we'll start, it's Monday, and on the first day what we do is we'll focus mainly on building the user interface for our application. So here on the left you can see we have a main screen. From the main screen, we can tap to do, and from to do, then we can enter the list of our to-dos. And rather than bother you with the entire application, how it's built, in this talk, I want to focus on a single computation that this application does. And that computation has the job of fetching the list of to-dos, and for each to-dos, it needs to fetch its assigned username, and then it creates some data that's by the user interface in order to render the DOM tree. So let's start with something very simple. Instead of trying to build an entire backend for our application in the first day, what we'll do is just, use some variable with some fixed data, and then we'll leave the problem of fetching to future Mattia. He will be more than happy to deal with that. So what we do here is a very simple. For each to-do in the list of our to-dos, what we do is find the user with the same ID. Then we stitch together the user information and the to-do information. And finally, we build the result array. In the end, our component just calls our function and gets our data and builds the React DOM tree, right? Very simple. Well, very simple indeed, but present Mattia really hates past Mattia because, turns out that actually fetching data isn't a synchronous operation. So that means that all the code that was written on Monday needs to be thrown out of the window and needs to be rewritten to use promises. So what we try to do here is we convert our computation, and now we return a promise instead of the list of the items. We call fetch to fetch the data from the backend. We'll convert the result response into a JSON. And then, as before, we'll loop for each item of our to-do array. We fetch its related user. We get the JSON. We stitch that together. We build the result array. So it seems like that you just toss in and there async and await keywords, and everything is fine, right? So do you think that is a great application right there? So raise your hand if you think that is this shippable code. Okay, so turns out that past Mattia isn't so great at coding, and it happens that loading the data takes too much time. And well, why does it take too much time? Well, by having a short session of debugging, we actually find out that that code that we have written is synchronous, but is sequential. So that means that a lot of time is wasted just waiting for the result of the previous computation, right? And can we do something to improve our performance? Well, yes, indeed. We can do something else while we are waiting for the result, right? And what we can do? Well, basically what we can do is whatever does not modify any external data sources and does not depend on the result of the computation that is running in the other task, right? So coming back to our application, we find out that there is this simple task of fetching a to-do list item, and that task, given a to-do object, can fetch its related user and do everything without even knowing what's happening to the other to-dos, right? We define a function that describes just that behavior, and then we define our main computation again, but this time, instead of using for and await keyword, we just build a list of promises and we start them all together and we wait for them all to be completed. So again, do you think that here we have solved anything? Well, there's another problem. Turns out that issuing all those requests concurrently isn't so great. And that isn't so great because there are a few issues. Mainly, if you see from the picture, you can see that the requests may hang too much. They are just here. And also, I had reports where lower-end devices even crash, because this approach is so memory inefficient that if you have thousands of to-dos, the device will crash. And also, if you think about it, it doesn't actually make any sense, because why give the browser more work concurrently than the amount of work the browser can do concurrently, right? So basically, we are looking here for a way to limiting concurrency. And we are JavaScript developers, so we know how to build JavaScript, and the first thing we may try to do is just rewrite our computation again, and write it so we do buckets of requests. We do 10 requests, wait for them all to be completed, and then do next 10 requests, wait them all to be completed, and do that again. But is that actually the real way to figure and to solve this problem? But because what happens if one of those 10 requests takes too much? What if one request takes 10 seconds and the other just some milliseconds? We are wasting time again. So a better way will be something like defining a work stealing approach, where you define an array of jobs that needs to be done. Here we fetch before all the to-dos. Then we define a concept of a worker, and that worker basically checks if there is some job to do in the queue, and it ensures that the job is assigned only to that worker and no other worker can pick up that job. And finally, it's run the job and store the result. And finally, we can optimize our code and spawn as many workers as we like, but we have full control on the maximum amount of workers that may run concurrently. And finally, last thing but not least, we need to wait for all workers to have completed, because when they all have completed, there is no more work to do. So again, do you think that we are ready to release our application? Nope. Well, there is one weird issue in our application. It seems like that going back and forward from the main screen to the to-do list screen results in an increasing time of loading every time we go into the to-do list screen. And even that may seem awkward, it actually makes a lot of sense, because when we go back from the to-do list screen, we do not interrupt the running computation. So that means that even not we are using that data, the computation is still running. So we need interruption, but really what is interruption? Interruption is basically a way for the outside world of the computation to request a graceful interruption of the computation. And the computation, upon a request of interruption, may do things like abort an HTTP request or release some resources that the computation acquired in order to be run, such as, for example, subscribing to DOM events. That is a resource that we need to dispose. And well, so in JavaScript, we have a solution also for that. We need to define an abort controller, and we need to hook up our component such that when our component mounts, we trigger abortion, then we get an abort signal from that abort controller, and then we can finally pass that abort signal all the way down into our computation until finally, after ages, you pass along strange function names, you finally get into your fetch request. And finally, you just pass in there a single variable, you know, JavaScript is great. And what happens is that upon that abort signal, your fetch request will get aborted. So do you think again that we are ready now to release our application? Yes, I think so. It's Friday, so why not release it right now? Well, we released our application, and it went also great and also well that, well, on Saturday, the backend broke. We had so many requests because our application was so successful that the backend became unreliable. And that means that occasionally the backend would fail. And you know, that means that we need some way in our application to handle that. And that is called resiliency. And to fix that, what we can do is just retry if our computation goes into error. And when to do that, what we do is just wrap our code into a while loop. We try to perform the computation. If it succeeds, yes, that's great. If not, we catch the error, then we wait some amount of time and we retry again. And obviously, that amount of time we wait needs to increase every time, because if that wasn't a fixed amount of time, you know, we were just adding more workload to our backend, right? And finally, after this busy week is Sunday, and Sunday is an exceptional day. By exceptional, I mean filled of unhandled exceptions. Well, because I can guarantee you that what we have seen so far is just the top of the iceberg, because there are a lot of things that may go wrong. We can have no connection, so we file to fetch. What about if we have a wrong JSON from the backend? Or what if our computation is somehow recursive and it reaches the maximum amount of code stack? Well, what's clear is that after a week of regular JavaScript development, I felt exhausted. Because what started as a really simple computation ended up being something like thousands of lines of code that actually makes no sense. And I also felt like that I spent more time fighting the platform, fighting the native JavaScript API, rather than building critical business logic for my application. So, acknowledging the current state of the art of defining computation, I would say that's a complete disaster. And well, I can already see some of you saying, well, that's not my problem. I use React Query, I use GraphQL, I use whatever I want. Well, the problem is that that is not just a problem for the frontend. That's also a problem for the backend. I'll say something that will make you want to check your code base. What happens if a client makes a request to your GraphQL API or your REST API, and then the client closes the connection? Does the computation on the server stops, or you use the regular promises, and that means that it's still running, even if the computation results will never get back to the client? And there are very much amount of problems like that. For example, we may have connection timeouts with the database. So we need to retry to connect to the database instead of just failing. And we may have also the same problem of limiting the amount of requests that our API wants to receive. And well, as said before, it's clear that promise isn't going to solve anything, because we had no control over execution. with promises, the computation already happened, and we had no way to implement a retry logic naively in the promise, and there were no interruption, and the promise doesn't know anything about concurrency. And if you're like me and you use TypeScript, you will also find out that there are no typed errors. Promise just types the successful return times. But what happens if your computation goes into an error? Well, so I sit upon that problem. I thought about it for a few days. And that problem seemed very similar to something that I already heard about. I realized that actually that problem is very similar to the problem that React Fiber tried to solve. Because, you know, even in React Fiber, there is that problem. What happens if we started rendering a component and it's child, but there's an update and that update invalidates the previous component, but we are still trying to render in a child, we need to interrupt. Or what if we are not maximizing the amount of work we are doing rendering or our component? Or what happens if our component goes into an error? Well, about that topic, there will be a great talk that will go deep dive into how fibers work and what actually they solve. And today I want to focus speaking about about Effect. And Effect is a library that is focused on structured concurrency and is optimized for ease of use. And Effect is baked by a powerful runtime, and in the Effect runtime is such as the one you're maybe familiar with the X for fibers. So basically you define a computation in a way, and behind the scene there is a fiber execution that does everything for us. Effect has 3 parameters, and these 3 type parameters are R, which stands for requirements, and then we have E that stands for errors, and A that stands for SSX. And basically, that 3 type parameters are very useful because by just looking at the type signature of the effect, we can know a lot about our computation. You know, with promises, you just know what's the successful return type. But with effect, you know what are the dependencies of our computation, what it may result into if it fails, and what is the successful return type. And the Effect API will also try to leverage as maximum as possible the inference of TypeScript to get rid of manual typings. So let's try to solve some of the promise problems with effects. One of the biggest problems we had with promises was that they weren't lazy. So that means the computation already happened, right? Well, with effect instead, you have a lazy data structure. That means that when you define your program, you are not executing your program. You are just creating a description of the program, what the program will do. And then you can execute that description of the program into the effect runtime as many times as you want. Here, for example, on the left, we can see that we defined our program. The program logs a value into the console. It eventually returns 42 because that is the question. And then we loop and we call unsafe run with to execute our computation 10 times. And as you can see in the log, we got the expected result. What you can also see here is that with effect, we do not return a promise. With effect, we return another data structure called exit. And what is it exit? Well, exit is a clear representation of the real-world computation, because real-world computation may success due to a value of type A, or may go into a known failure that is somehow recoverable of type E, or, you know, shit happens. So your computation may die for some unknown reason, or may fail because an interruption was requested from the outside world. So, you know, past week wasn't so great. So let's start a new week. But this week, let's get things done using effect. So again, on Monday, we'll focus on our synchronous computation, and we start with sync effects. Let's implement a basic sync function, and to do that, to construct a synchronous effect, we use effect.sync to lift a function into an effect, and we can return the list of to-dos from our variable. By just hovering the mouse here, you can see that inference did its job, and the effect has no requirement, no possible errors, and may return a list of to-dos. We can also do the same for our get user computation. Our get user computation will take in the user ID, and we'll just call effect.sync again and look up into the user's array for the user ID, and then it will return our user. By hovering at the type signature of our computation, we can see that, well, there's that undefined in the success type. Well, maybe we don't want undefined in the success type, right? So what we can do here is lift the, use the error channel and move that undefined into the error channel. So we have explicit error that are fully typed. So first thing we do is define a class that is just a value that represents our error. You can also use regular plain objects if you're not into classes. And that class has user not found error. It gets a user ID, that's the user we have not found. And then we update our computation. As you can see, the first part of the computation is exactly the same as before. We look into the array. But then we do the strange thing that we call effect.flatmap. And what does flatmap? Well, some of you familiar from the functional world may know what that computation does, but basically flatmap allows you to chain to computation. Basically, you can construct a new computation based on the successful return value of the previous one. So here, if we succeed in getting the user, what we do, we construct a new computation that needs to be executed, and that computation will be succeed if the user is present, and we will fail if the user is not present. Again, inference did its job, and now what happens is that we have an effect that has no requirements, may fail into a user not found, and will return a user if found. So again, we can see that we already improved, because now we have type information that really helped us. And thanks to typed errors, we can also have some help from the TypeScript inference. And that means that if we use the previous defined computation inside other functions, for example, here we define again our fetch list item computation gets the user and then stitches together the user and to-do, we can see here that inference is doing its job and is still pointing out that your computation may fail and may early out due to a user not found error. And again, we can finally define our main computation, which is get list items that fetches all the to-dos, and then again using flatmap, we look into the successful result of get to-dos, and we chain a new computation that is run for each to-do, and for each to-do, we run the fetch list item to-do function. And that's it. We have built our synchronous computation with effect. So now let's move on, and it's Tuesday, so let's fetch real data from the backend. And you know, unfortunately, many of the browser APIs are natively using promises or callback. But no worries, because you know we can use effect.try-catch-promise to transform those promises or those callback functions into effect instances. Here we see that we pass in a lazy promise, because if you remember, we need to be able to execute our effect as many times as we want. So we need to have a lazy promise. And since promises aren't typed in the error channel, we can also provide a function that types somehow the error. For example, here we wrap the error into a fetch error. You know, the world isn't so easy. There may be lots of other kind of errors, like the body that we are fetching is not JSON, so there is a JSON body error. Or maybe the result isn't a to-do array, so it's not a valid to-do object array. And what's really great about Effect is that the API really compose, and in the error channel, we can see the list of all the errors you can have when executing your computation. And I'm sure that you will love to see 265 errors in your main entry point of your application. So obviously, there are also ways to handle errors because shit happens, but we can recover from that. Sometimes, for example, if we don't find our user, what we can do is just return some other string instead, because maybe our user interface is fine anyway if we say deleted user number 3 or user number 25, because maybe it's not the main point of our user interface. Or what happens, if you remember when we spoke about exit, we said there are also unrecoverable errors. And we can use or die to move the error from the typed channel to the untyped channel and make that error unrecoverable. Well, we have written that in Effect, but that was, again, sequential. That was not concurrent. So, do you remember how painful it was with JavaScript? We had to rewrite almost the entire computation in order to make that concurrent and parallel. Well, with Effect, we just changed the name of the combinator. Instead of for each, we use for each par, and that's it. Because thanks to the fiber-based runtime, the parallelism instead can care by the runtime. We just tell the runtime, okay, we want a parallel computation. And that's it. But again, we have the same problem. You know, there are so many requests running one concurrently to the other. And so what we can do is then limit concurrency. And again, do you remember how we implemented a work stealing approach? Well, in Effect, you can just tell the runtime the maximum amount of parallelism is 5. And the runtime will just limit itself to run maximum 5 concurrent computation and no more. So, what about the interruption? Do you remember that we have to define an abort controller, pass all along the abort signal, and finally reach the fetch request? Well, interruption is built in Effect, and its runtime fully understands interruption. That means that every small block that you build your application by default is uninterruptible, but if you define your small building blocks as interruptible, for example, if we use a sync interrupt to construct an interruptible computation, Effect will ensure that when the top-level computation asks for interruption, the cleanup effect, which is the controller.abort in this case, will be called for sure. Well, we also had to retry in case of errors, right? Well, even retries is a concept that is built in Effect, because like in React there are error boundaries, in Effect there is retry schedule. So there is this schedule data type that you can use to construct a retry logic. For example, here I built the same one that we built before by doubling each time the time we wait after an error requesting. And we have also advanced the concept, like, for example, if the server returns a JSON body error because there is malformed JSON, maybe it doesn't make any sense to continue to ask the backend, because maybe we get again another malformed JSON. So we can tell the schedule to do not retry upon that error. And finally, it's Sunday, and well, there are no exceptions. for now, so we can invest more time in some problem that we may have in the future, something like dependency injection. And dependency injection in Effect is built by first you have to define the shape of your dependency. For example, here in TypeScript, we define a user service, and that user service has a get user computation, and that user computation basically, as before, takes in the user ID and returns either the user or not found error. But you know, TypeScript information gets erased out when you compile your code. So in order to have something we can hook up our JavaScript code when referencing to the dependency, we create a tag. That's basically just a symbol that refers to that user service. And then we use the function service with effect in order to access that service implementation, and based on the implementation we call get user, and then we can do our computation as before. What you can see here is now that that error parameter we spoke about before that now contains the user service. So by looking at the type of our computation, we see that the computation requires a user service, it cannot fail, and it may return a string. So again, as we did for the error channel, even dependency stuck. So that means if our computation uses another services, for example, the to-do service, we define the to-do service, we define a tag, and when we access it, now the type signature also shows the to-do service. So our computation now is fully described in whatever it requires. And that's really great because, you know, then you can provide a different implementation for your services. For example, you can have a real implementation that's used in the actual application and a dumb implementation that returns fake data that's used in test, if someone does test, because, you know. And finally, we get also to see that now our requirements became never, because we fulfilled all the requirements of our computation. So basically, Effect solved a lot of problems. Effect solved the control over concurrency. Effect provided a way to retry logic, to interruption, to concurrency control. We had type errors, and we also had dependency injection. And that is all thanks to a Fiber runtime. And the Fiber runtime is so powerful that actually there is a lot more in Effect. There are a lot of other data structures that use Effect as its core, but actually provides a lot of functionalities. For example, we have hubs for pub/sub of events, or we have pool-based streams. They are kind of different from RxJS stream, but the same idea. And we spoke today in the conference about OpenTelemetry, right? Effect has built-in support for tracing, and there is also a package that integrates OpenTelemetry with Effect, and you can use that in the backend or in the frontend, because you know Effect is just some way to substitute promise. And there are a lot of things that Effect can help you to do. So does it mean that tomorrow you should rewrite your entire application with Effect? Well, no. What I hope that today I gave you some insight about the problem that Promise has and your computation may have, and how Effect try to solve that problems thanks to its Fiber runtime. So where to go from here? Here's a QR code that points to the code base that we have seen today. Here we can find the to-do application written with Effect. And with that, I want to thank you all for your time. And here there are some information. You can find Effect at github.com/effects.core. And there's also an active Discord channel. Today also I met someone from the Effect Discord channel. So if someone already joined or someone wants to join, please come say hi. And again, Thanks you so much for your time, and see you next year.